It's a great pleasure for me to be invited to lecture at the summer school. And I was very much hoping when Peter invited me in December, I believe, that we would be in Russia now. We had never been in Russia, me and my wife, and we were so looking forward to it. But well, there is always a next time. I mean, we will visit Russia and Moscow in the future. And instead of Moscow, the excitement has become one of giving this online lecture to you. I should confess that I never gave a lecture online in the past. And so this is an exciting journey in its own right. The topic for us today, as you don't see actually, because my why is my slides not in sync with what is visible there? Oh, just a moment. Zoom కళ్ళకరా స్లోనే ఉండు. Oh, sorry. Just there. This should fix it. No, ఇక్కడ చేసా. ఇప్పుడు ఇది ఏ మోడ్లో ఉందిరా? Okay, but my window is no longer అంటే let's go to the Zoom. ఇక్కడ ఏదో చేశాను, ఇక్కడ VMixలో ఉండేవాడిని నేను. Yeah. Sorry about that. So that tells you with my inexperience with this thing. So the topic for today is recoverable concurrent algorithms. The topic that I have decided to lecture on is a little more general than what I announced, which was just about locks, and I wanted to make it a little more general. And given that we have a lot of time, nearly 3 hours, we should be fine covering a broader range than what I had announced earlier. So what are recoverable algorithms? Well, I'll be saying what recoverable algorithms are, I mean, in a few minutes. Concurrent algorithms have been studied for at least 55 years, since the middle 1960s until now. So for about 55 years, there has been a rich literature on concurrent algorithms. Recoverable concurrent algorithms, at least in the flavor that I'll be describing today, are relatively new, more like, 5-6 years. So whether it is traditional concurrent algorithms, and I'll explain what the distinction is between traditional and recoverable. So whether it's traditional concurrent algorithms or recoverable concurrent algorithms are simply intellectually very interesting, very exciting, very challenging. They're a pure joy. And it is this excitement of concurrent algorithms and recoverable concurrent algorithms that I'm hoping to share with you. So it is true that multiprocessors, multiprocessor programming are going to be increasingly important in the future. So we should study them because they are important in the future. But perhaps even more important than that is that they are really fun. And it is that aspect, the fun aspect, the excitement aspect, the challenge aspect that I would want to convey to you, communicate to you during this talk. Okay. So let's begin with an understanding of the traditional model of a multiprocessor. By the way, there's a little bit of delay, maybe even as large as 3 seconds, 4 seconds between what I do here and when it is showing up on the screen. So I need to get used to this bit of lag. Hopefully it won't bother you and it won't bother me. Okay, so here I display the traditional model of a multiprocessor. So it's a multiprocessor. So clearly, there are many processors. I have shown here processors P, Q, R, and so on. Each processor has got its set of registers. I call them A, B, etc. There is also a register PC, which is the program counter. So this is the register set of this process. And each processor, of course, also has got a cache. It has got a cache. And all the processors are interconnected through this interconnection network. And from the interconnection network hangs the shared memory. This is the shared memory, and it hangs off the interconnection network. Okay. So that's the look of a multiprocessor. The essential features of our multiprocessors that we assume are that processes or processors are asynchronous. Processors and the processes that run on these processors, they are asynchronous, which simply means the rate at which a processor executes the instruction may change arbitrarily over time. So a processor may be very fast at the moment and become very slow the next moment, and its speed relative to other processes can vary arbitrarily over time. So there are absolutely no guarantees about the rate at which a processor executes its program, and that's what asynchrony means. The other important assumption of our model is that caches are always consistent with the shared memory. So, so if a processor writes a particular value 5 for a variable x, not only does it get reflected in the cache of that processor, but it also migrates to the shared memory, and the shared memory at all times is in sync with the caches. Okay, so this is for those of you who were at Michael Scott's lecture yesterday, and probably, I mean, a large number of you were there. This is one important difference between the architectural low-level details that he described in the model that he dealt with, and the high-level model on top of which we will be designing algorithms today. So in our model, henceforth, in the rest of this lecture, assume that caches are always consistent with and in sync with the shared memory. Okay, so there are never any stale values in the shared memory. Perhaps this is achieved through fences. Perhaps it is achieved through hardware cache coherence protocols. However it is done, we assume that caches are in sync with shared memory. Okay. So how does this memory then actually work? So let us look for, let us understand that. And in fact, as I explain how values migrate from shared memory to cache, and what synchronization instructions we assume are made available to the processors, I want you to be aware of a particular term that has a lot of significance for us. And that term is what appears here, and that term is this remote memory reference, RMR. I'll explain what RMR is in the next few minutes. You will understand what it is. So to illustrate how this entire model works, pretend that there is a variable, let's call it x, and let's say x's current value is 5. Maybe this value is not in any processor's cache yet because nobody has bothered to read this value yet, let us say. Now, as I do this illustration, I'll also take this opportunity to explain to you the meaning of 4 of the shared memory instructions that I would like you to understand and that we will be using in our algorithms. All right? So the first instruction, 1 second. I have, fortunately, 2 people in my audience right in front of me, right in front of my eyes, my son and my wife. and they are trying to give me some feedback about the video or the audio. Let me find out what it is. What is it?
We're not able to see what you wrote on the slide, I think.
You are not able to see. Maybe I'll ask the question to Alexei and Peter. Alexei and Peter, I wrote something on my slide. For instance, for shared memory, I wrote and with a value of 5.
Yeah.
Well, I do see it, but
Yes,
I see the studio view. Yeah, just give me 1 second, because we see something which is projected to the studio, and I don't see the view of the audience. Let me check.
Yeah, we saw it with the lag.
It's such a big lag.
Yeah.
I wrote like a minute, 2 minutes ago.
That's
You are able to see X with 5.
Yeah, I think it's coming
Peter?
with a lag. Same thing. Yeah, just 1 second.
A lot of lag maybe, because I wrote it 2.5 minutes ago. Because if there is such a big lag, then I probably should make some adjustment. Let us see. I'm just about to write another thing, and let us see how quickly it appears at your end. Audio sync is fine, because I'm able to hear them real time. Okay, there is a variable y and a value 8. I just wrote y and 8. Are you able to see that? Can you tell me as soon as you see it, Alexei and Peter?
Yeah, we
Yes,
see it.
I see it.
Yes.
We see it.
You saw that?
Yes.
Okay, good. Let me proceed. You both should feel free to interrupt me if what I'm saying is completely out of sync with what I'm hoping to write on the iPad. Okay.
Yeah. People from chat also write that they see what you write.
They are able to see on the chat. Okay. Fantastic. Okay, so let's proceed, and feel free to interrupt me as necessary. So suppose there are 2 shared variables, x and y, with values 5 and 8, as I have written here. And okay, here is the first. I said there are 4 instructions that I want you to know about. So let me introduce them even as I introduce other concepts. Suppose this processor P reads. Suppose this processor P reads the variable x, the shared variable x. So in this case, since x is not already in P's cache, it will be brought from the shared memory through the interconnection network into the cache, and then into the register A, because that's where we said it should be written. Okay, so it goes through the interconnection network all the way into the cache. And A also gets the value 5. So this read instruction, to fulfill this read instruction, traffic was generated on the interconnect, and value had to be brought all the way from the remote shared memory into the cache, all the way from here to here. So this particular read instruction is considered a remote memory reference. It's considered a remote memory reference, RMR for brief. All right. Now, suppose just for fun, suppose the process reads x again, let's say into register B. Now x is available in cache. Therefore, this read will be fulfilled just by the cache. It will be fulfilled just by the cache, and it did not have to go all the way to the shared memory. So it did not have to traverse the interconnection network. So the second read is now a remote memory reference. It is not a remote memory reference. It won't cost anything at all. It's cheap, whereas an RMR is very expensive. Now let us say this process here, this process R, let us say writes some value 10 into X. So the writing of this value will cause a traversal of the interconnection network, because the X will have to be invalidated, and the X here will have to be changed to 10. And therefore, this write is an RMR. Write is an RMR. It's a remote memory reference. Now, continuing our example, suppose this process reads X again. Now X is no longer available in the cache, and therefore it will need to be brought all the way from the memory into the cache, and therefore this read will again be an RMR. All right, so that is the notion of a remote memory reference or an RMR. And in the process, I explained to you two instructions. What are they? Read and write. Of course, these are the common instructions with which we are abundantly familiar. But there are two other synchronization instructions that hardware commonly supports that I would like you to be familiar with, because we will be using them in our algorithms. One instruction is CAS. So, for instance, let's do the instruction. CAS stands for compare and swap, as I'm sure you know. Compare and swap X, let's say A, B. So compare and swap take arguments. The first argument is a shared variable, X in this case. And the next two arguments are simply process registers. Process registers. I said A and B in this case. And how does this instruction work? I'm sure, most of you are familiar with it, but I do want to go through this basics so that we won't lose each other when we discuss algorithms. So the compare and swap instruction compares the current value of X with the value in the register A, and if they happen to be the same, then it changes the value of the variable to whatever B is. Okay, so if X and A are the same, then X is changed to B, and the return value would be true. I lost it. Okay. The return value would be true. So in this case, what happens? Well, current value of X is 10. The current value of the register A is 5. They are not the same. And in that case, the value of X will not be changed, and the return value would be false. So a return value of false will happen. That will be returned. So A will become false. On the other hand, suppose A did have 10. Suppose A's value was 10 when CAS was issued. In that case, if since X's value is the same as A's value, 10 and 10, X would be changed to the value in B, which is 5. And therefore, X would become 5, and true will be returned. So A will assume the value true. A will get the value true. So that is how the CAS operation functions. I hope that's clear. That's how the CAS instruction works. I hope that's clear. Well, the eraser in the eraser is too slow in Keynote. Okay, so to understand the FAS instruction, let's do A gets FAS. xb. Fast stands for fetch and store. So if you do fetch and store on the variable x and you pass the argument b, what does b have? 5. So what happens is that value 5 will be written into x, and whatever is in x, whatever was in x will be put in the register little a. Okay, so in this case the value in b is 5, so that will be put in x, and what was in x, which is 10, goes into a. So that is the result of fetch and store. So it stores the value in x, and whatever was in x will be stored in the register a. So you can simultaneously store a value as well as learn what value was there in the variable just before you stored. So that is the purpose of a fetch and store instruction. Okay, so any instructions such as write or cast or fast, which modify the shared memory, because they modify the shared memory, they will always be considered remote memory references. On the other hand, the read instruction will be considered a remote memory reference only if the value that you are reading, the variable, is not already present in your cache. If it's already there in your cache, then the read is not a remote memory reference. So that is the traditional model of an asynchronous multiprocessor as far as we are concerned. In this traditional model, there are no crashes. We assume that processors do not crash. They can only slow down and speed up, but they never crash. What does that mean? That simply means that if a processor is executing a program and it is at instruction 10, it could stay at instruction 10 for 1,000,000 years if it wants to, or maybe only for a nanosecond, or for 1,000,000 years. But it will surely execute that instruction eventually. Okay, it will never crash. So that is the traditional model. Okay, so algorithms, for the past 55 years have been designed for, there have been innumerable algorithms designed for asynchronous multiprocessors for this model. And I will now move on to the model that is fairly new. The model for which recoverable algorithms are being designed in the last 5-6 years, at least in the style that I'm going to describe today in our class. So this model is essentially the same as what we discussed so far. All of the elements that I have said so far continue to apply. But on top of that, in this model, there is a possibility that processors might crash. There's a possibility that processors might crash. But if so at any point in the execution, at any point in the execution, an individual at any point in the execution, a processor could crash. Any processor could crash. For instance, suppose processor P crashes at some point. What does a crash mean? To us, what the crash means is that all the registers associated with that processor are wiped out. They're wiped out. They assume arbitrary values, including the program counter. So even the program counter is lost. So what does that mean? That means when a processor crashes, it completely loses a sense of where it is in the program that it is executing. Okay? And all the values in the cache associated with that processor are wiped out. What does that mean? That means that if it needs to bring in, when it eventually restarts, if it reads values, it'll have to bring them again from the shared memory into the cache. Okay. So when a processor crashes, therefore the things to remember are that the registers are wiped out, the cache is wiped out, but we assume that the shared memory is persistent. So all the variables that reside in the shared memory they remain intact. Okay, so that's good, because something has to live, you know. If everything dies, what can you do? There is hardly anything we can do. So the shared memory is persistent, and that assumption is justified because, as we know, and as was abundantly made clear in Michael's talk, there is increasing interest and increasing availability of persistent non-volatile memory, random access memory. Excellent. So once a process crashes, so suppose this process P crashed and all the registers got wiped out and so on, what we assume is that the processor, the processor and the processes running on the processor, they eventually restart. Okay. The delay between crash and subsequent restart can be arbitrary, but the restart will eventually happen. And when the restart eventually happens, we want, when the restart eventually happens, when the process eventually restarts, we assume that the process will be put back into the protocol. Okay. So the same thread, the same process comes up in the same avatar. It comes up in the same avatar after the crash, and it is put back into the protocol. But where in the protocol will it be put at? Well, at the time it crashed at a particular point in the protocol. But we lost that point because of the crash, right? Because of the crash, the program counter got lost, and therefore we lost a sense of where we were in the program at that time. So after the restart, when the process is put back into the protocol, it is put back into the protocol at the start of the protocol. At the start of the protocol. But here is the challenge. So a crash occurred, all registers were wiped out, restart has happened, the process has been put back at the start of the protocol, and now the challenge is we still want the process to proceed in such a way as though, when you look at it from a high level, nothing bad really happened, and things have gone on just fine. That is how it should look from the top, from a high level point of view. So if you are able to design algorithms with that intuitive property, then you would say your algorithm is a recoverable algorithm. Okay. So that is the crash restart model. So there are two flavors of crash restart model. One flavor is when we assume that at each crash event, an individual process crashes. For instance, maybe P crashed and maybe the system ran for some more time, and a little later process R crashed. And then maybe the process P restarted. And then maybe process Q crashed. And then maybe Q restarted. And then maybe R restarted. Right? So a crash event is associated with the crash of a single process. That is one flavor of the crash restart model. Another flavor of the crash restart model is the system-wide crash model. In this model, when a crash occurs, the entire system crashes. Meaning, when a crash occurs, all processes crash simultaneously. So the registers of all of the processors are wiped out. The caches of all of the processors are wiped out. But the shared memory is persistent, and therefore it survives the crash. It is intact. And then subsequently, when the system comes back up, each process will restart the protocol from the beginning at a point of its choosing. Maybe this restarts after 1 nanosecond and this restarts after 10 seconds. Because it's an asynchronous system, they might all restart at different times, but when they crash, they all crash simultaneously. So that is the system crash model, system crash model. So we would be interested in designing algorithms that can tolerate these crashes and restarts for either flavor. For the system crash model, for the individual crash model, we would want to be designing algorithms that tolerate these failures. Algorithms that tolerate crash failures are called recoverable algorithms. Okay. So that then is our model of computation. So to quickly recap our model, our processes are asynchronous, our caches are coherent, they are consistent, they stay consistent with the memory at all times, and the instructions to manipulate the shared memory that we will be using in the rest of this talk, and actually in most of the algorithms of the literature, the instructions that you commonly come across are these instructions: read, write, cache, and fast, which I have described to you. And we have the notion of a remote memory reference. A remote memory reference is any of these instructions when they have to traverse the interconnection network, which is a very slow thing. You don't want to be using up the interconnection network and introducing traffic on the interconnection network, because if you do, and if all applications do that, then that will be choked up. And also it will lead to a lot of delay, because fetching the value all the way from the distant memory into the cache is a very slow operation. So you don't want to do that. So we would be wanting to design algorithms whose RMR complexity, the remote memory reference complexity, is as low as possible. You want to design algorithms that make as few RMRs as possible. Okay, so those are the elements of the traditional model. And when you introduce crashes, the points to remember are that a crash wipes out processor's registers and cache. And when a processor subsequently restarts, program counter is set to the start of the code of the protocol. And another important point, I didn't write it here, but you should remember, is that the only thing that survives the crash is the shared memory, because we assume that it is on a persistent RAM chip. Okay, so that is the model. And for those of you, which is probably most of you, who are there at Michael Scott's talk yesterday, there are two important distinctions between the model that he was dealing with and the model that we are dealing with today. And the two important differences are our caches and memory, as I said, are consistent at all times. So the memory is in sync with cache at all times. And secondly, for Scott yesterday, if a process crashed and subsequently restart happened, then the process will not, for him, it will not come up in the same avatar. Okay, it's gone. It won't come up ever again in the same avatar. But for us here today, when a process crashes and it subsequently, the system restarts, the process comes back in the same avatar and re-executes the protocol from the start. But we want to create the illusion as if nothing bad, no failures happened at all, and the entire system is running smoothly. Okay, so that is the distinction between yesterday's model and today's model. So this is a good time to pause for a minute or two, so that if any of you have any questions about the model with which we will be dealing with going forward, I would like to hear and clarify. Alexei, Peter,
Okay.
if you hear any questions, please relay them to me.
Well, I don't see any questions from the audience. But maybe just a quick question for me. So these differences between the model used by Michael yesterday and your model, does it have any like practical motivation to use this particular model or that one? Like which of these two are closer to reality?
he is closer to reality, I'm closer to the dream world, in short. But I'll expand on that. That's a good question. So when you look at the bare bones of a multiprocessor, of course, I mean, Intel could be architecting things one way, someone else could be architecting things one way. The cache coherence could be maintained a particular way in one system and in some other way in some other system, and there could be all these variations. And it is true that cache coherence is, of course, maintained anytime a multiprocessor supports cache. But what cache coherence means and how well the memory is in sync with cache could vastly differ. And in general, I mean, they don't have to be in sync. I'm assuming that they will be in sync, but they don't have to be in sync. But here is the point. If you want to force them to be in sync, there is always a way to do that. Like the fencing instructions and so on, you can do that to force them to be in sync, but it's a costly thing to do. It's a costly thing to do. True, but suppose I give you the ability to fence as you want, and I tell you, hey, like I'm telling you now, hey, the cache and the memory are in sync, and so that's a great thing. Enjoy that benefit. But just because I give you that benefit, does that make things easier for you to design solutions for the problems that you really care for? I'll argue that despite giving you this freedom, despite giving you this benefit that caches and memory are in sync, your difficulty, your challenge of designing correct algorithms for problems that you care about is still not going to be easy. It's still challenging.
Easier.
Slightly easier. So perhaps the way to do things is assume, like we do in this talk, that caches stay in sync with memory, and design algorithms for the problems that you care about. And once you have designed those algorithms with this assumption in mind, you know that you can enforce this assumption by using fences liberally. But you don't want to use fences liberally because you don't want to introduce delays in your program. And therefore, then modularly think about where do you really need fencing and where can you get away without a fence while maintaining the correctness of your program, right? So you are therefore thinking of the solution in two steps. One, designing the solution on top of the simplified assumption. And once you have that solution, which by the way is not going to be easy, but once you have that solution, to then translate that solution into the exact machine model by introducing fences, but only as necessary and as provably necessary. So, so that is what one really has to do. Shall I move on?
The process identifier, yeah, just the second assumption, if you concerning the avatars, the process identifiers, so the process which we covered.
Concerning the avatar.
Yeah.
The second assumption, that we make here, that the process will come back in the same avatar. If that is something that you can support, then that's a good thing, right? I mean, let's say Prasad is the process and he's going along and he met with this unfortunate crash. And if there is a way for Prasad himself to come back on and just carry out his business as if nothing happened, and if that can be done, then that is a thing to welcome.
Of course.
And therefore, this is a thing that we would like to be able to do. And so if we are able to do, as we will be in the algorithms that I will discuss, that's a good thing.
No, the question is how realistic is this assumption?
How real is this assumption? I will answer it in two parts. One, it is a standard assumption made in the design of these algorithms. So I'm not making any unusual assumption here. Standard in the literature. And second, I'm not too practical a person to authoritatively tell you whether it is highly realistic or not. But it is a standard assumption made in the literature and makes a great deal of sense to me. So it seems fine to me.
Okay.
Does that make sense to you, Peter?
Yeah, of course. Yes. Please
Yeah. Very good. And by the way, the interactivity when I'm writing and when I'm moving the laser pointer, were they appearing with an irritating lag to all of you, or they were mostly fine? Were they following my words?
No, it looks okay for me. I hope it's the same for the audience.
Can you quickly ask the people on the chat? I mean, can you ask the audience to see whether it's mostly okay?
Yeah. Could you please confirm in the Telegram channel if you see the slides and the pointers? Okay. Okay, so no reaction. What's going on?
By the way, could you repeat, please, in a few words, definition of RMR?
RMR. RMR stands for Remote Memory Reference. So if you are a process and you execute an instruction, and if that instruction causes the machine to fetch something from the memory or the interconnection network into your cache, then it is considered a remote memory reference. But if your instruction does not cause a traversal over the interconnection network, then it is not considered an RMR. For example, if you are reading a variable for the first time, then it is not there in your cache. So it needs to be brought from the remote memory into the cache. So it will be considered an RMR. But once you brought it into the cache, if you read it many more times, all of these times it is just fetched from the cache. So those reads are not considered RMRs. But if you are writing or you are caching or you are fashing any of these operations that actually change the value of the variable, then those operations will be considered RMRs because they will have to invalidate all the caches in all the processes and they'll have to plant the new value in the remote memory and so on. So fast, cache, write, they're all always RMRs. Read is RMR sometimes, but not when the value is present in the cache. Clear?
Yes, thank you for the explanation.
Yeah.
I think the audience confirmed that everything is fine. So you can.
Oh, wonderful. I'm happy to hear that. And so let me move on. So with the model understood, the next question is, we understand the model, so let us solve some problems. But then what are some of the interesting problems to solve, right? So for the traditional model, let's focus a little bit for the traditional model because we need to understand a few concepts very, very well before we can hope to design recoverable algorithms, because they are harder to design than the traditional algorithms because you have one more element to address, namely crashes. So if you look at POTC or disk, POTC, by the way, is the main staple conference for distributed computing, concurrent computing. And if you look at what happened in the last many, many decades in the general area of asynchronous process synchronization, I would say most of the results fall into two buckets. One bucket is this, where we are trying to implement useful shared objects, for example, a shared queue or a snapshot, a shared tree, red-black tree, for example, or a hash table. So these are shared data structures, shared objects that you would love to have so that your applications can can access them. But these are not, of course, directly made available by the hardware. So you will have to implement them in software. So how do you implement interesting and useful shared objects like queues, snapshots, etc. On your multiprocessor, on your asynchronous multiprocessor? So this is one very different class of problems that people have shown, on which there has been a great deal of research in the past many decades. A second bucket of problems that attracted a lot of research is designing solutions, designing algorithms, protocols for exclusion problems. Mutual exclusion being the king of all of the exclusion problems. It's the most important one, but there are other types of exclusion problems like readers, writers exclusion, group exclusion, L exclusion, and so on. And so how do you design algorithms, efficient algorithms for these problems? So these two broad classes of problems are what captured the attention of people. And in the past, the goal was to design algorithms for these problems in the traditional model, in the non-crash traditional model. And the current goal in the past few years, of course, people continue to do that, continue to work in the traditional model, but there has also been research on designing recoverable algorithms for the crash restart model. So that has become an interesting topic of research in the past half a dozen years. Okay, so with this in mind, let us look at some of the problems in. Let us look at what the excitement is in these two classes of problems. Okay, so what's the first class of problems that we will look at then? Implementing useful shared objects, right? So let's spend half an hour, something like that, maybe until the break on that topic. Whatever it takes, maybe a little less, maybe a little more. Okay, so implementing shared data objects, or shared data structures, shared data objects. What does it even mean to implement a shared object such as a shared queue? What does it mean? What does it mean if I ask you, hey, implement for me a shared queue, what does it mean? It's very simple. It simply means design code. What operations does a queue support? It supports enqueue and dequeue. So obviously you should, to design a queue simply means you should design the code for enqueuing and dequeuing, right? So you design a code for procedures enqueue and dequeue. So if a process P wants to enqueue an item X in the queue that you are implementing, it will execute this enqueue PX procedure, and by executing this procedure should have the effect of enqueuing this X in the queue object that you have implemented. Likewise, if a process wants to dequeue an element from the implemented queue, you should supply a procedure dequeueP that it can execute to draw an element from the queue. So designing these two procedures amounts to designing a queue, right? All right, that of course is sensible. But I should tell you what the correctness criteria are. If I don't give you any correctness criteria, then we can write any crap for the enqueue and dequeue procedures and then call that our queue implementation. So obviously that won't do. So we obviously need correctness criteria. So what are these correctness criteria? There are two. Of course, these correctness criteria are entirely up to us. But I will discuss two specific criteria, which are really strong guarantees. They're so strong guarantees that you would love to be able to implement objects with those guarantees, because if you are able to do so, then these objects are going to be fantastically usable. They are as good as having these objects implemented atomically in hardware. Okay, so what are those criteria? Those criteria are precisely what I have listed here: linearizability and weight freedom. Okay, so but what do these words mean? What does linearizability mean and what does weight freedom mean? That's what I'm just about to explain now. Okay, linearizability simply means, look, suppose you implemented a queue like we just discussed. If you want to enqueue an item into the queue, what do? You will execute the enqueue procedure. Is the enqueue procedure, are you going to be able to execute the enqueue procedure instantaneously? Obviously not. It's a procedure. It has lots of instructions. So to enqueue a single item into the queue object, into the software queue object, you have to execute this procedure, which is a lot of instructions, and therefore the execution of this procedure, your enqueue operation, will span over an interval of time. It's not an instantaneous operation. It spans over an interval of time. Likewise, if you want to dequeue and you execute the dequeue procedure, it's not instantaneous. It's going to span over an interval of time. But even though these operations, enqueue and dequeue, or whatever other operations you have implemented, even though they are not instantaneous, the linearizability criterion requires that these operations, which actually span over an interval of time and are not instantaneous, the criterion requires that they must still appear. They must still appear as if they took effect instantaneously at some point within the interval during which they actually executed. Okay, so linearizability essentially says each operation, enqueue or dequeue, or any other operation of the shared object that you have implemented, even though in reality it spans over an interval of time, it should still appear to take effect instantaneously at some point within the interval in which the operation actually took place. So that's what the criterion says. It's important to very clearly understand this criterion so that we are able to actually design algorithms. And so let me illustrate what this could be like. Suppose you and I have implemented a shared queue. Okay, if you and I have implemented a shared queue, and let's say this is the time axis, and let's say a process P comes and enqueues an item 5 into the queue. Assume that the queue is initially empty. Okay, assume that the queue is initially empty and that a process has come and enqueued 5. So to enqueue 5, it would have executed the enqueue procedure, and maybe that procedure started here and ended here. And okay, and let's say another process concurrently is executing an enqueue operation, and let us say its enqueue operation is enqueue 10, and let us say it started at this point in time and took a long time and it ended there. Okay, and as these two processes are enqueuing, let us say another process comes along and it is trying to dequeue. It's trying to dequeue, and let us say another process comes and it is dequeuing, and let's say that its dequeue takes place over this interval of time. Okay, now to help us understand linearizability, I'm going to ask you a question and I want you to ponder over it. Suppose that this dequeue, when it used your implementation, you supplied the enqueue and dequeue procedures. You and I wrote an implementation, and this dequeue, let's say, happened to return 5, and let's say this dequeue happened to return 10. Suppose. So suppose this is the actual history that actually manifested when the implementation was used. My question to you is, does this history look acceptable to you? Put differently, does this history meet the linearizability criterion that I just explained to you? Does it? Think about it. I'll pause for just 10 seconds before I talk. I'm not waiting for your verbal answer, but I do want you to ponder. Okay. Indeed, it is linearizable. It is good. It is linearizable. And why? How do we reconcile it with the condition that I just explained? Linearizability means that each operation should appear to take effect at some point in time within its interval, and the resulting order of operation should make sense, right? So, can we pretend that this NQ took effect here, this NQ took effect at this instant, and this DQ took effect at this instant, and this DQ took effect at this instant? If they indeed took effect in those instants, does the resulting history make sense to us with respect to the ordinary FIFO of semantics of a queue? It does, right? Because, well, if you look at the points, NQ5 happened first and then NQ10, and therefore when a DQ happens later, it should return the earliest item NQ'd, which is 5, and the next DQ should return 10, and it did. Okay? So this history was completely acceptable.
Yeah. Prasad?
Yes.
Yeah, so maybe
Please
next time we should give a bigger lag if you ask a question to the audience, because I think there's also a few seconds delay between you talking and the projection on the for the viewers.
I see.
So okay, but there was one answer which was negative, but well, now you explained that it was an incorrect response.
Okay. I hope the person that asked understands why it is linearizable, and maybe they can tell you that over the chat or ask again. And I'll keep your suggestion in mind, certainly. And if I forget, remind me. Keep reminding me. Thank you.
Yeah.
Okay. So suppose, on the other hand, when our implementation was used, these DQs did not return 5 and 10, but suppose they returned 10 and 5. Suppose this fellow returned 10 and this fellow returned 5. All right. If that happened, now tell me whether this history looks acceptable to you or not. Or equivalently, is this history linearizable or not? Please remember that the particular linearization points I have marked on the intervals were to help explain the previous history. So it is clear that the same linearization points don't explain the current history, but maybe there are different linearization points that we can now give to reconcile with this history, to see that this history is okay. Or maybe not. I don't know. I'm again asking you. So think whether this history is linearizable or not. I'll give you this time 30 seconds. I'll look at the clock so that there is enough time for you to reflect.
Okay, we have one answer, yes.
Very good. So, indeed, the answer is right. Whoever answered yes answered correctly, because you can explain this history. For instance, how about the following linearization points, right? You want to explain that this fellow, this fellow getting 10 is explainable. So linearize 10 first, NQ10 first, and then NQ5, and then, I mean, if you linearize the DQ and then linearize DQ to this point, then 10 got NQ'd first, and then 5 got NQ'd, and then the DQ therefore returned 10, that's fine, and then the next DQ returned 5, and that's fine too, right? So that's great. So this history is linearizable also. I'll give you another example, and you tell me whether that is linearizable or not. Suppose this DQ returned, the first DQ returned 10, and let's say the second DQ returned nil. Or how about this? Yeah, the second DQ returned nil, and the first DQ returned 5. Is this linearizable? I will, without pausing, I'll explain that this is linearizable. Why? Well, we may have to fix the linearization points differently now, but let's do that. But remember that you have to put the linearization point of each operation within its own interval, okay? But that's not hard to do for this history. Let's suppose this is linearized here, and suppose 10 is linearized, suppose 5 is linear, DQ is linearized here, and suppose this DQ is linearized here, and this NQ is linearized here. Now, do you see that the responses are explainable? 5 got NQ'd, and then DQ took the 5, and then another DQ came. At this point, the Q has nothing, and therefore it returned nil, and then the NQ put 10. So this is fine. This is linearizable. One last example. Suppose instead of 5, this DQ returned 10, and this DQ, suppose, still is returning nil. Is this history linearizable? On this, I'll give you 30 seconds. So this fellow returning 10 and this fellow returning nil. Is this linearizable? Okay. It is not. It is not linearizable. Why? Because to explain this 10, of course, I mean, this NQ will have to be linearized to some earlier point. Let's say it's linearized to that point, and then let's say you linearize DQ to this 10. But where will you linearize this NQ? You have to linearize it to some point within its interval. But wherever you linearize it, that NQ will be visible because this DQ is strictly starting after this NQ ended, and therefore this DQ cannot miss that NQ. So its returning nil is not explainable. So this particular history is not linearizable. Okay? And so now that we understand what linearizability means, when we say that an implementation is linearizable, what we mean is that when processes use the implementation, then in an asynchronous setting, when they use your implementation, no matter what history happens, it is guaranteed to be linearizable. So all histories of a correct implementation have got to be linearizable, and only if that is the case, you will call the implementation correct, linearizable. Are we together? I want to, Alexei and Peter, I mean, if there are any questions in the chat about linearizability, I would like to take that question.
No, not right now. I think it's
excellent. Excellent. By the way, how do you implement linearizable objects? It's very easy. Very easy, because suppose you want to implement a linearizable queue. All you need to do is just implement a sequential queue, a queue that can only be accessed by one process, and then put a lock around the queue. So if anybody wants to, so now, I mean, let's say there are 100 processes that could access this queue. If anyone wants to access this queue, they are expected to first, let us say, get the lock on the queue. And once they get the lock on the queue, they have exclusive access to your data structure. So they will manipulate it. They'll put they'll do the NQ or DQ, and then they'll give up the lock so that someone else can do the queue operation. So what would be the linearization order then? The linearization order will be the order in which a main processes acquire the lock. Okay? So such an implementation is trivially linearizable. But what's the drawback? The drawback is you implemented it using locks. And what is bad about implementing using a lock? Well, I mean, the clear drawback is if you have the lock, because you are trying to do an operation on the queue, and I too want to do an operation on the queue, I'm forced to wait until you give up the lock for me to do my operation, right? And we are dealing with an asynchronous system where processes can arbitrarily speed up and slow down. So if you have the lock and you became very slow after you acquired the lock, then you're forcing me to wait. And I don't like waiting, and therefore I don't like the solution. So the message then is realizing linearizability is very easy if we are allowed to use locks, but we do not want to use locks, and therefore we want some other criterion that properly captures the requirement that the difficulties that are caused by locks should not be there in our implementation. And what is that criterion? And that's the next criterion. That's the next criterion I'll explain. But before I explain that criterion, let us try to devise an algorithm that implements a toy. This is really a toy problem, okay? No one in the right mind would want to do it in practice, but this is a fantastic problem to train our minds towards these concepts. So what is this toy problem? I want you to implement a shared object that supports the simple operations read and write, okay? Read and write. Implement an object that supports read and write. Using what? Using read and cache operations. No one in the right mind, I mean, would do that, because read and write operations are almost universally supplied. I mean, they're always supplied by the hardware, so why would you want to implement them using a fancy operation like a cache? But this is just a toy problem. So what would be an implementation of this without using locks? So here is the algorithm implementation that I have given. So the idea is very simple. We are trying to implement this object A that supports read and write, right? Okay, so we will, our implementation will use a single shared variable X, which essentially keeps the value of the object. Let's say the current value of the object is 5. So if someone wants to read A, it's very simple, just read X and return it, okay? But if you want to, if a process P wants to write, let's say it wants to write a value 10, what should it do? Well, normally, because the write operation is not provided, but the cache operation is provided. So can you make use of the cache operation and read operation and somehow implement the write operation? Easy. What do? What's the natural thing to do? Read X, you get 5, because that's what X has currently. And now you say, well, I mean, if it still has 5, change it to what I want. What do you want to change it to? You are trying to write 10, so you try to change it to 10. So you are saying compare and swap 5 with 10. So how does this implementation work? You would read 5, and then you would go to this cache instruction, and if the value is still 5, it'll change it to 10, and true will be returned. And is returned, you are quitting the loop, because I mean, you planted the 10 that you wanted to write, so you are done, right? So that's great. But what can happen? What can happen is between the time you read 5 here in this instruction, and before you do the cache instruction, Isn't it possible that someone else has come and changed it to, let's say, 8 because they were writing 8? So when you do cas 5 comma 10, your cas will now fail because the 5 is different from the 8. So the cas will fail, and therefore you did not succeed in planting your value 10 into this variable x, right? So what do you have to do? Well, you wanted to write 10, but you were not successful. So what can you do? Go back, read x again, and then try to swing its value from whatever it is to 10. So you keep doing it, you keep doing it until you succeed in planting the 10 into x. So that is the solution. So it's not using locks, but it's a different style solution, and it's a solution that satisfies linearizability. Okay, but this is not satisfactory, right? Because even though it's not using locks, can't a process be stuck in this repeat until loop forever? It can be stuck forever, right? Why? Because maybe, for instance, maybe the value is 5 and you want to write 10. You read 5 and you try to change it 10, but before you do that, someone had changed it to 8. Therefore, your cas will fail. And so you will again read 8. And before you change the 8 to 10, somebody changes it to 15. So this could be happening ad infinitum, right? So you might never complete this repeat until loop. So a process trying to do a write operation could starve, unable to complete its operation ever. And that's not nice. So that brings us to the next requirement that we would like implementations to satisfy, and that is wait freedom. This condition says the beautiful thing. It says every process should be able to complete its operation in a bounded number of its own steps, regardless of how its steps interleave with the steps of other processes. Okay? So when I execute the NQ procedure or the DQ procedure or any other procedure that the implementation is supporting, I should be able to complete that procedure in a bounded number of my own steps without regard to whether you are also concurrently doing operations on the shared object or not. Okay? So this is a beautiful property. And henceforth, when I say we want an implementation, what I mean is we want an implementation that satisfies both linearizability and wait freedom. Satisfying one or the other is easy, but satisfying both of these properties simultaneously is really, really challenging. And a lot of literature, research in POTC, DISC, and all distributed computing conferences, algorithmic conferences, a lot of literature is on such non-blocking linearizable implementations. Okay, just to give you a sense of the excitement of this challenge, but again, with a simple example, I'll revisit the toy problem. So what I show here is the solution that we have so far, right? I don't know why this procedure, by the way, is not properly indented. Well, imagine that it's moved. So this is the algorithm we have so far, right? This code is not wait free. So we don't like it. So I now give you 2 complete minutes to think about an implementation for this very same problem. What was the problem that we were trying to design a solution for? We just want to implement a shared object that supports the simple operations read and write using the operations read and compare and swap, right? So that's the problem. And this is the solution we have so far. We don't like this solution because of this loop. And we instead want a wait-free solution. And I'm now giving you 2 full minutes. And I want you to get rid of this looping code and come up with some very simple code that will make it weight-free and linearizable, of course. Okay. 2 minutes.
If you have some solution, please write to the Telegram chat, because it's interesting. No. Or maybe some words about such problem.
Sorry, my microphone was muted. Yeah. I've just muted my microphone. No. Yeah. So the problem is how to implement a weight-free write using cas. I think you are not supposed to use other primitives.
Correct.
Yeah, so the challenge is to make it weight-free. Now we have a log-free, right? So how to transform it into weight-free?
Yes, dear participants, you're free to.
Yeah, you can share your solutions in the chat.
The 2.5 minutes elapsed. So should I?
Yeah, I think you should give maybe 30 seconds more. I think.
I'm happy to. I mean, sure. Yeah. If there
because
are solutions,
someone is typing.
Yeah, we'll wait. You tell me when to start.
Okay. Okay, so the solution is just do read then cas once. If it fails, just complete the operation.
Fantastic. That's a beautiful solution. Here is the solution that one of you posed. The read is just as before. Just of course, I mean, x has the value, so read x. X has the value, so read x and return it as before. But for write, here is the tricky solution. You read x. Suppose you want to write 10. You want to write 10. You read x. Suppose it was 5. You read 5. So you try to change the 5 into a 10. So there are possibilities. One possibility is when you do the cas instruction, the value is still 5, and you successfully change it to 10. In this case, of course, the write operation successfully took effect. And where would you linearize it? You would linearize the point where you did the cas, because that's where you planted the value 10. So the write takes effect there. So that's great. So you are done. But what about the other possibility? The other possibility is it was 5, set 5, but somebody else came and changed it to, let us say, 8. Someone else came and changed it to 8. And then you did cas 5, 10. And what happens to your cas now? It'll fail. It'll fail because the value is 8 and it doesn't tally with the 5. So it will fail. But if it fails, what do you know? What you know is that your write operation is write 10, right? And to implement your write operation, you did 2 instructions. One is read you read and you got 5, and then you cast, and when you cast, your cast failed, and it's because its value at this point is 8 or something other than 10. But if it is 8, then what? When did x become 8? Somebody must have made it 8 after you found it to be 5. So it assumed the value 8 at some point after you read 5 and before you did the cast. Here it became 8, right? So that point must have been the linearization point of some fellow's right who was writing 8, right? So that right operation took effect here, and your right operation overlapped with that right operation. So what can we now linearize right operation to? Our right operation unfortunately did not succeed in installing the value 10. But then here is the brilliant observation. It is that you have the option of linearizing this right 10 operation just before the successful right operation of 8. So it is as if this fellow wrote 10, but no one in the world ever was able to see it because it was immediately occluded. It was immediately overwritten by some other fellow that wrote 8. Right? So this cute implementation where even if the cast fails, you simply walk away is a correct implementation. Okay? So that's fantastic, and I'm very glad that the audience have come up with this suggestion. So let's move on. But here then is the lesson. The lesson is, even for the simple problems of just implementing read and write operations, when I give you the rich read and cast operations, it was still tricky to come up with to satisfy both linearizability and weight freedom, right? So now let me give. So you must think that, oh my God, I mean, if it was tricky even for this toy problem, for a real problem, it must be way trickier. And indeed, that is so. Just to get ourselves going with this excitement, let me now give you a different problem, which is no longer a toy problem. This is a real problem of interest, and one that will have a very cute solution. But I just want to appreciate. I want us all to appreciate how challenging and exciting, I mean, these algorithms can be. So fine. So what is the problem? The problem is implementing an object called snapshot. Okay. So I have described here what a snapshot object is, but let me also graphically help you understand what this object is. A snapshot object, you should think of a snapshot object as an array, okay? As an array of n locations. As an array of n locations. Okay. So it's an array of n values. It's accessed by by a process called a scanner. Okay, by a process called a scanner. Scanner wants to get a snapshot of this entire object, meaning the scanner wants an instantaneous picture of all of the values in all of the n locations. He wants to get all of the values as an instantaneous picture, as a snapshot. And then there are n writers. Okay, n writers. So what can the ith writer do? The ith writer can only change the ith component. The ith writer can only apply the operation write iv, which simply means write the value v into the ith component of the snapshot. So if this is the ith component of the snapshot, write iv operation, which can only be applied by the ith writer. So the ith writer is the only one that can change the component I. So write IV operation will write V into the ith location of the snapshot. And what can the scanner do? The scanner can only apply the operation scan. And what does the scan do? Scan simply returns all of the n values in the snapshot object. Okay? And
yeah, Prasad, we have only about 2 minutes left to break. Maybe move to questions.
Very good. In fact, I mean, in 1 minute, I will leave it at the right point for people to think about something in the break. We are right there. We are at a good point. Okay. So we want a linearizable and weight-free implementation of the snapshot object. Okay. So how do you do it? That is the puzzle. That is the puzzle. And the hint for the puzzle is what is written in blue here. I'm telling you, hey, it is possible to implement the snapshot object using just 2 arrays, call them A and B, both of which have just n locations, and additionally a single Boolean variable. And I'm giving you a hint of what that Boolean variable, what its purpose could be. Scan is active. So when the scanner is active, it's true, and at other times it is false, roughly. Okay. So using this idea, see if during the break you can come up with an implementation of a snapshot object. I'll leave the slide on most likely, or unless I need to change some slide for myself. So an implementation during the break, or think about it, and after the break, I'll tell you a very elegant, exciting implementation of this. Alexei and Peter?
Yeah. Maybe we should recall that you only assume that there is a one scanner and multiple writers.
Correct. So just as I noted here, remember that there is only one scanner. One scanner S and n writers W1 through Wn. And remember that only the ith writer can change the ith component. No one else can. Okay. So these conditions implement the snapshot object. Linearizable weight.
Then do we try to implement weight-free or log-free snapshot?
Weight-free.
Weight-free.
Weight-free. Linearizable and weight-free. We'll start our question after the break.
Okay, thank you.
Okay, thank you.
Thank you. See you soon.
Let's start the second part of the lecture. And before we start, maybe some questions from the participants.
Or answers.
And while participants think about questions, a question for me, Prasad, what do you think? For what real applications or algorithms weight-free approach is preferable instead of log-free? In what cases we must use weight-free algorithms?
Yeah. So my sense of it is often the case that for many data structures and data objects, qualitatively, linearizability and weight-free, if you can have those two conditions both satisfied, qualitatively, I mean, that is the thing you can ask for. However, the complexity of a weight-free implementation for many data objects, data structures, tends to be not very good. And therefore, you will have to, in those cases, when you are not able to get satisfactory time complexity for weight-free linearizable objects, you should settle for some inferior guarantee than weight freedom. However, there are two occasions when, weight freedom, two ways in which weight-free research has immensely influenced things and I think, realistically useful. One there are some problems, including, for instance, the snapshot solution that I'm just about to show you, where, you get an extremely time efficient, space efficient, and elegant weight-free solution. So it is only because we have the notion of weight freedom and we went after it with great appetite that we are able to design such solutions. And so where you are able to get them, they are the most sought ones, and we should get them. And secondly, the notion of weight freeness is applicable in many settings. Like, for example, in this very talk, when I will talk about recoverable mutual exclusion sometime soon, there will be a requirement where you will, which will be a weight-free requirement, which is a highly sought and desirable and achievable property. So there are situations where the weight-free notion is natural, desirable, and can be realistically implemented. So it is good to be aware of what it is. It is good to be aware of what the general techniques are to make that possible. And it's also good to be able to prove lower bounds that would tell you conclusively that you should be probably thinking about ways of toning it down to other conditions.
Okay,
Does
thank
that
you.
make sense?
Very, very interesting. Yeah.
So do the audience have any solution for the snapshot problem?
No, it seems like not.
Okay, that is fine. In fact, it is unfair to give you only half an hour and ask you for a solution. This would be, a good exercise for a few days, and then when you reflect deeply, you will see the solution. But I'll show you the solution. By the way, now we are in the second half, and it is my hope to show you a lot of algorithms and giving you good intuition for these algorithms. And at times, showing you why they are interesting. We cannot, of course, go into rigorous proofs of correctness of any of these algorithms, because that would just be way too time consuming. Proving a normal algorithm itself can be time consuming. Proving a concurrent algorithm correct is particularly very, very challenging. And so we won't go into proofs, but it's my hope to give you either the excitement or the intuition or both with a lot of algorithms in the second half. But I won't be spending too much time on any one algorithm. Peter?
Yeah. Just there is a suggestion. So the suggestion by Andrei is so the writer needs to first read B, then set the flag, then read A. Well, I'm not sure why the writer sets the flag of scan is going, but okay. And the reader writes to A if bit is not set, and otherwise to B. Okay, so there's something about it. So the reader, I think maybe there's a mix between the writer and the reader. Okay, let me try again. So the reader, the scanner, needs to first read B, and then set the flag, and then read A. The writer writes to A, and if bit is not set, and otherwise to B. Okay. I think there is something there, but I'm not sure how to interpret this.
Very good. So here is how I will deal with this problem now. To discuss any individual solution and would take a lot of time. So I would very much encourage this person as well as others to come to the discussion meeting tomorrow, the discussion group tomorrow, so that we can have a chat about their ideas for solution and how they are. And secondly, so with that said, I will now give the solution. My idea is to just impress upon you how simple and elegant the solution is. You will not believe why it is correct, by the way. I will not be able to convince you why it is correct, but believe me, it is correct. And what I want you to do after you look at the algorithm is think tonight. And until we meet tomorrow, think why this algorithm is correct. Or if you think it is not correct, try to break it. Okay. Alternatively, if you have ideas on maybe a simpler algorithm or a different algorithm, come up with those ideas also tomorrow. And we will try to chat about all of those. But with that said, here is the algorithm. First I will just visually tell you what is going on just with a drawing, and then actually display the algorithm also. But remember, I want you to understand what the algorithm is, and I'm not going to explain why it is correct because that will be way too long, and that is deferred for your own reflection and discussion tomorrow. Okay, so as I have written here, the algorithm, the snapshot object is going to be implemented using a Boolean, which is this Boolean scan, and scan is active. That's that Boolean scan is active. Scan is active. Let's abbreviate it to SIA, and then the two arrays A and B. Okay. Now, let me tell you what the algorithm is. The writer, the ith writer that wants to write the value v in the snapshot component I, that this procedure, this operation is implemented as follows. The writer will simply write v in AI. He will write v in AI, and then the writer will check this flag. The scanner is active flag. If that flag is true, the writer will write v into BI also. But after writing v in AI, if the flag is false, the writer will simply walk away. That's it. That's the algorithm for the writer. So let me repeat. Writer will write v in AI and then check this flag. If the flag is false, the writer is done. Over. If a flag is true, then there is just one additional, which is write v in BI also. That's all. That's the algorithm for the writer. And what is the algorithm for the scanner? Here is the algorithm for the scanner. The scanner will come and first write true in the scan is active Boolean flag. He'll write true, and then the scanner will write bottom, meaning nil, in all the locations of the B array. The scanner will write bottom in all the locations of the B array. And then the scanner will read all the locations of the A array and remember the values he got in the A array. So let's say he keeps a local array S. So into S, what does the scanner do? He reads all the values in the A array and keeps them in the local array S. After that, the scanner will write false in this flag. Scanner will write false in the scan is active flag to indicate that the scan operation is essentially over. It's not completely over, but it's essentially over. Okay? After that, the scanner will read the B array. So when the scanner reads the B array, what are the two possibilities? What might he find at BI? Either the scanner will find bottom, which he had written just before, he wrote bottoms in the beginning, remember? So he might find bottom in BI. If he finds bottom in BI, then he is going to tell himself, hey, whatever I read from AI, which I kept in my SI, is good. I'll go by that, he'll think in his mind. But if in BI he finds a value that is different from the bottom he had written, then he'll say, hey, I got a non-bottom value in BI and I'm going to prefer that to whatever I got from AI. So he is going to change SI to what he got from BI if he got a non-bottom value. Understand? So by the time he finishes reading the array BI, so he updates his image of SI, which was initially loaded with what was in A, but where he finds non-bottom locations in B, he modifies the S. So he therefore formed this array, local array S, as a composite of the two arrays A and B in the way I just described. And it is this array S that he composed that the scanner will return as the instantaneous snapshot of the snapshot object. Okay? So just to see for yourself that what I just told you is indeed what the algorithm is, let me just very quickly go over the, let me just convince you that that's the actual algorithm and that I didn't misexplain and you didn't misunderstand. So the shared variable we use are the two arrays A, B, and the Boolean scan is active. The writer procedure is simply write V into AI and then read the scan is active Boolean, and if that is true, write V in BI. Okay? And how does the scanner work? Scanner will start off by setting scan is active to true, and then he goes through the n components of BJ and sets them to bottom. And then he goes through the n components of the A array and reads them into his local array S. And then he sets scan is active to false to indicate that the scan is essentially complete. And then he goes through the B array, and wherever he finds a non-bottom element, he will take that to be the SJS value. But if it is bottom, then he will keep whatever he got from AJ. Okay? So at the end, he returns the S array as he composed it, as the value of the snapshot. So that's it. That is the algorithm. Okay? And it's obviously weight-free. I mean, there are no waiting loops here. So it's obviously weight-free. Its time complexity, scan's time complexity is off n, and writer's time complexity is off 1, just 3 instructions. So that's great. The space complexity is off n. So this is time and space optimal. It's clearly weight-free. But how do you convince yourself that it's linearizable? That's not going to be easy to convince yourself that it is linearizable. I tell you it's linearizable, but try to prove that it is linearizable. This will take a lot of reflection. So I invite you to think about the proof of linearization in the night today before we meet tomorrow. So let me pause here for a minute. If there are any questions, Alexei, Peter, you can relay any questions there are from the audience. Again, I'm not expecting you to be convinced of the linearizability during the talk, but if there are other questions, I would be happy to answer.
So let's wait, because there is a considerable lag between the between us and the audience.
Okay.
No, it seems that there are no questions for the moment.
Very good. Very good. So I hope that our discussion has convinced you that implementing linearizable weight-free objects is intellectually challenging and interesting, and where we can do it efficiently, it's a very welcome and very useful thing. And where we think we cannot get efficient implementations, of course, I mean, it would be very interesting to prove lower bounds on time complexity or space complexity to convincingly to convince ourselves that it's not just because of our inability that we were not able to design a good algorithm, but I mean, intrinsically it is hard. So there is therefore, I mean, rich scope for research in this area, and understandably, I mean, this has been a very rich area of research for decades now. So moving on, so at this point, we should wonder, hey, I mean, if this is this hard to design a snapshot algorithm, and remember that we designed a snapshot algorithm only under certain assumptions, that only writer I can modify component I, and only there is only one scanner. What if I relax those assumptions? Then, I mean, the problem becomes harder. The algorithms probably become even more challenging to design. So if things are this hard to design, weight-free, if it is this hard to design weight-free linearizable objects, then I mean, what are we to do? I mean, humans are all, of course, always looking for simplifying things. I mean, if at all possible. So in that context, Maurice Herlihy came up with a wonderful result about 30 years ago, and he showed this beautiful result that every shared data object, so not just the snapshot, not just a queue, not just a fetch and add, not just a counter, any data object that you can think of can be implemented to be linearizable and weight-free if only you have available to you cast, read, and write instructions. So using these instructions, you can implement any object you like to be weight-free and linearizable. Isn't that exciting? That's Herlihy's universality result. And in light of this, well, I mean, what inspiration can we draw from this? Look, so far we discussed implementations in the traditional model when there are no crashes and recoveries, restarts, right? Now let us think about designing a linearizable weight-free implementation for the crash model, where individual processes can crash at any time and restart at any time. So, so if we want to design shared objects in this crash restart model, then what objects, what problems, I mean, what object should we be wanting to implement? Should we be wanting to implement a queue? Should we be wanting to implement a stack? Should we be wanting to implement a snapshot, a tree, a hash table? Which one? Well, this universality result gives us, I mean, obviously there's only so much that we can do. So this universality result says that a shared variable that supports cast, read, and write operations is very special, because if you have such shared with them, you can implement anything you want in life to be weight-free and linearizable, right? So if a shared variable supporting cast, read, and write is that great, if it is that great, then if we wish to implement recoverable objects, why don't go ahead and implement a recoverable object that supports these operations, cast, read, and write, right? So that should probably, I mean, the first problem that should interest us. And so that's what we will do now. Okay, we will try to implement a recoverable object that supports cast, read, and write. But here is a little thing. It turns out a recoverable algorithm implementing all three operations, cast, read, and write, is going to be pretty hard to convey in a talk like this. So I'll take the simpler problem of designing a recoverable algorithm that implements just the cast and that implements a shared variable just the cast and read operations, leaving out the write. Okay. We can also do cast, read, and write, but it's out of the scope for our talk today. So let's implement a shared variable that supports cast and read, and we want the algorithm to be a recoverable algorithm. What does it mean? It should stand ready to do the right thing, even if there are crashes. Right? Okay. So what is the challenge? What is the challenge designing a shared variable that supports cast and read in the face of crashes, right? What is the challenge? Here is the challenge. The challenge is, suppose the value is 5, and suppose you are a process and you come along and you try to change 5 to 10 with a cast. Okay, and you want the response to go into your register A, let us say. So the following can happen, right? The value is 5. You want to cast 5 to 10. So what happens to your cast? It will succeed, right? Maybe it'll change it to it'll change it to 10, and it will return true, right? It will return true. But where did the return value true go? It went into little a. What is little a? Little a is your process register, right? So now imagine the following, that just after you did the cast, you crash. Then the return value true, which was present in your register, got lost because all your registers are wiped out because of the crash. Remember? So you now crashed. You had no idea whether you failed just before the cast operation or just after the cast operation. You have no idea. And now imagine that some other process Q comes along, and some other process R comes along, and so many other processes come, and they all change the value from 10 to 11, from 11 to 19, from 19 to 18, from 18 to 186. Who knows? The rest of the processes are merrily going along and changing the value. And at some point, let us say, you who had crashed, restart. You restart and you come back to your protocol for the cast operation which you were in the middle of before the crash. And what is the situation of your cast operation? You had executed it and it returned true, but you have no idea that you executed it, and you have no idea whether it succeeded or not, whether the response was true or false, because you lost it. That is the reality. So what will happen now? Should you think that your cast, you failed before your cast and therefore you should re-execute it? Or should you think that maybe you did it and the response was false? Or should you think maybe you did it and the response was true? The only thing you have to consult, at least in the way I have drawn things so far, is this variable x on which you are going to do the cast operation. But if you now consult its value, so many other people have come and changed it, and you have no idea what had happened to your operation, whether you crashed before or after, and if you crashed after, what the response was. So that is the predicament, that is the difficulty. Are we clear in understanding what the difficulty is? This is just a rhetorical question. I'm not going to wait. But if you are, if you need any clarification, be sure to send something in the chat box so that Peter or Alexei can alert me. All right. Not hearing anything. I'll move on. So let's look at the algorithm. Look, given the predicament, our bright idea is going to be that we will use a central variable, let me call it x, and the central variable will maintain three fields. It will maintain who changed this variable last, so the process name, and it will also maintain a sequence number, and it will maintain the actual the value of interest that is stored. So it stores the value of interest along with which process stored that value and the sequence number of that process. Okay, and so that's one thing about the representation you should know. And the second thing about the so given that, first see the following. Remember that we want to implement cast and read operations on the implemented object, right? So let's say A is the implemented object. A is the implemented object that is supposed to support read and cast operations, and X is a variable used in the implementation in order to implement A. A is a recoverable object that we are trying to implement. X is just a normal object. It's not a recoverable object. So when someone wants to do a recoverable read on A, their job is simple. They'll simply read X. And so they get the process ID that wrote the value and the process's sequence number as well as the real value, U. And so they'll simply read U. That's easy. So doing a read on A is very easy. How would you do a read on CAS? Well, let us see. So when a process P wants to invoke the read operation on the object A, on the recoverable object A, it will supply a sequence number. So whenever a process invokes a fresh CAS operation on the object A, it gives a newer sequence number, a bigger sequence number than before. And the CAS operation, of course, has two arguments, right? It's the old value and the new value. And the intention of the CAS operation is that if A currently holds the old value, then it should be switched to the new value and true should be returned, otherwise false should be returned. That's the intention of the RCAS object, as we know. Okay. So how does the process proceed? How does the process P proceed? Well, an additional time for an additional idea. The additional idea is, look, suppose at the moment the value of X is Q I U. Suppose this is the value of X at the moment. What does it mean? The real value of A is U. The real value of A is U. And this value was written by process Q. And process Q's sequence number at the time of this writing is I. That's what it means, right? Okay. We want to be sensitive to the fact. That just after process Q wrote this value U in the variable X, process Q could have crashed. That could have happened, right? And if it did happen, when eventually, maybe 100 years later, when Q wakes up, it will need to recognize that it indeed performed the CAS and it succeeded, and that its CAS's return value is true. So how would you communicate that to Q when it might wake up 100 years from now? How will it be able to figure that out? Because during these 100 years, the value in X could change from this million times, zillion times. So how would you convey to Q that its sequence number, that its cache with the sequence number I indeed had succeeded? So in order to make that possible, every process, for instance, process Q has a persistent variable called risk Q, where when it invoked a recoverable cache operation with sequence number I, it would have initialized it to I comma false. And if ever anybody sees any evidence that Q's sequence number I operation succeeded, they would help Q understand that, learn that by writing I comma true in the place of I comma false in the risk Q variable. Okay, so that is the purpose of the risk Q variable, for Q to be helped, to be intimated that its cache operation succeeded if it did succeed. All right. So given that understanding, you will now find it very easy to understand the rest of the algorithm. Okay, so P starts off by, how does P start off? What should P do? Well, if P is initiating a new cache operation with sequence number seek, then P simply writes seek comma false into its result variable, initializes the result variable to seek comma false. And then it reads Q, and then it reads X, and suppose it gets QIU. Now, the possibilities are the following. One possibility is the value U in X and the value old are different. Suppose old is 10 and U is 5. U is 5 means the current value of the object A is 5. So if you are attempting to cache from 5 to something else, then this cache should fail, right? So it's very easy to linearize such a cache. So if U happens to be different from old, then this cache must fail. So you will indeed return false and you are done. So that's a simple scenario. The other scenario, so when will you come to this other scenario? When will you even come to line 8? You will come to line 8 only if U and old are the same. So suppose they are the same. Suppose they are both 5. If they are both 5 and new is also 5, new is also same as old, it's also 5, then what does it mean? The current value of the object is 5 and you are trying to switch 5 from 5. So don't do any action. Don't change anything in X, because what you want it to become is what it already is. So without doing anything, without disturbing X, you can simply return true, and that would be a legitimate thing for you to do, because the object already has that which you want it to have. Okay? So if old is new, just return true. If neither of statements 7 and 8 is true, what does that mean? That means old is, U and old are the same, but new is something else. For example, new could be 8. So in this case, what should you do? In this case, you know that you are about to change Q comma I comma 5 into, you are about to change this into P comma C comma 8. That's what you are wanting to do. But before you change, what is one thing that you must be sure of delivering? You must help Q understand that its installation of 5 is successful. So how do you do that? You will simply go to, risk Q, and you will change I false into I true. With what? With a normal cache operation, not a recoverable cache operation, but with a normal cache operation, you will just change I comma false to I comma true to inform Q that its operation has succeeded. Now that you have informed Q that its operation has succeeded, you now have the freedom to change X, which you now do. You change X from QIU, from QI5 to P, C, new, P, C, 8 in this illustration. And if you succeed, you return true. If you fail, you return false. What other thing that can happen is you do the cast, you get a response, but before you return the response, you fail. But that's nothing to worry about, because if you install P, C, new, if you install P, C, new, then anyone else in the future that will change it will inform you here that your cast with the seek has succeeded. So in light of that, what should the process P do when it crashes and it restarts and attempts to recover from the crash? So when a process P restarts after a crash, it wants to know whether its previous operation succeeded or did not succeed. And how can it know? It will simply read X. So what is an X? Could be some value that's installed by someone else, or it could be a value that is installed by P itself. But regardless of what it is, whatever it finds in X, if it finds Q, I, U, it will help Q understand that its operation with sequence number I has indeed succeeded by doing this cast, where it is telling Q that its operation I has succeeded. And so remember that this Q could be process P itself, in which case P is helping itself. If Q is different from P, then it's helping someone else. In any case, it is now going to check its res P, and res P, if it is ever the case that P had succeeded successfully, then by now res P will reflect a true value. If P had not succeeded ever, then res P will still have false. So by consulting res P, it knows whether its cast operation succeeded or did not succeed. And therefore, it's able to recover properly after the failure, even if its restart after the crash occurred a million years later, and within this time, zillions of operations happened on the object A. So this is a simple algorithm because we are only implementing cast and read. But if you want to implement cast and write, then it becomes substantially more complex. But this gives you a flavor of how a recoverable algorithm, how a recoverable implementation of a shared variable, shared object can go. This field, by the way, is very nascent, and if you find it interesting, there is much to pursue. Let me pause here for a minute before I move to the next topic. So far, what did we do? We said of the two big problems that received a lot of attention in the POTC community. One problem is implementation of shared objects, and second problem is exclusion problems. But so far, we discussed the first problem, namely implementation of shared objects. We looked at traditional implementations of certain objects, the toy object and the snapshot object. And now I showed you a recoverable shared object that supports cast and read. So with this, our discussion of that first topic, namely implementation of shared objects, is over. I'm just about to move to the study of recoverable exclusion algorithms. And before that, let me pause for a minute if there are any questions. Video.
I don't see any questions for now. So maybe I have a quick question on the interface.
Sure.
So your implementation of a cas read object. So you assume that the cas operation comes with a sequence number.
Correct.
And you put it in one of the as one of the parameters of the cas operation. And the question is whether
Correct.
it is actually necessary for this implementation. Maybe you can use some local counter instead for the sequence number as a local variable of the implementation instead of putting it as an interface.
Some choices are possible. But ultimately what you need is, suppose you are the invoker, suppose you are the application that's issuing these cas operations. There must be a way for you to clearly communicate whether this is an invocation of a new cas operation, or you are asking about a cas operation that you had done in the past and you want to know the status of it. And there has to be that has to be disambiguated. If it is a new operation that you are executing, it will need to have some ID associated with it that is distinct, so that the implementation understands it to be new operation and can accordingly answer you. So some sort of disambiguating that is what is necessary. Sequence number is just one mechanism by which you can do that, but there are other ways, you can similarly address that issue.
Mm-hmm. But doesn't this somehow contradict the initial assumption you made about the model, where when you say that the process crashes, its program counter is also destroyed? And to me, the sequence number as an argument of a cas operation is a part of the program counter.
No, in terms of implementation, that's why you are asking whether the seek can be made somehow a local persistent variable, I suppose, so that you can hide it from the interface. Is that your goal? Hiding it from the interface? Yeah. So we can do that, like you suggest. You can have a persistent local persistent variable that is internal to the implementation, and then deal with it that way, so that you don't see the ugliness through the interface of this.
Mm-hmm.
But maybe we should take it offline and are into the discussion room.
Yeah, let's move on. Sorry.
Yeah. Very good.
One little question from me.
Yes, please.
Have you evaluated your atomics and compared with regular operations as are implemented in the software?
Say that again. Atomic and can you repeat?
Have you evaluated the efficiency of your atomic operations?
No. No. When I say no, let me be clear. Just the way I am, I have never implemented any of my algorithms ever in my life. in the sense that my own personal interest is strictly algorithmic, and have never had the opportunity or the training to do this other stuff, practical implementations. Having said that, let me also say that there are teams, including the team in CMU, where they are working on similar algorithms. In fact, the algorithm that I just gave you, most of it is from their work, but there was a subtle subtle bug, in that algorithm, and which we fixed. And their algorithm is for cast read, and our algorithm is for cast read and write. But that subtle bug, has been fixed here, and the cast read and write algorithm is a more complex one. And they have one too, and we have a more efficient one which we submitted for publication. But all the details aside, I personally have not tested anything. And nor am I in the habit of doing that. But there are teams that have been working on exactly algorithms like this and have been testing it. I would refer you to that work, because I don't consider myself knowledgeable at all to talk about practical realities and the times.
Okay, thank you. I understand.
Very good. So moving on, let's go to, yes.
It's stalling.
No. Yeah. Let's go to exclusion problems. Okay. The most important problem, fundamental problem, is mutual exclusion. Because if you have mutual exclusion and you don't care about non-blockingness, then there is pretty much everything. That's an exaggeration. Everything is always an exaggeration. But there are most things you can do, and you can do most things you can do. For instance, as we discussed, if you care about implementing linearizable queues, linearizable snapshots, linearizable hash tables, so long as you don't care for weight freedom or non-blockingness, if all you want is linearizability, you can do it if you have locks. So locks are, as we know, are tremendously useful in practice. And therefore, a lock is abstracted by the mutual exclusion problem, as we all know. And so there have been dozens or a bunch of dozens of algorithms, mutual exclusion algorithms in the past for the traditional model. And so it's no wonder that we should be interested in a recoverable solution too for the mutual exclusion problem. And but to get to be able to wrap our heads around a recoverable algorithm, it's first instructive to actually look at a very efficient a traditional algorithm for mutual exclusion, and then we can build on that intuition for recoverable algorithms as well. So let me very quickly go over the mutual exclusion problem, which Dijkstra defined way back 55 years ago. This is the earliest concurrent computing problem that probably, that was ever worked on. And as you know, in this problem, which abstracts an exclusive lock, processes are in the remainder section if so long as they are not interested in the lock. And once a process gets interested in the lock, it executes the try section where it competes with other processes for the lock. And when the process actually acquires the lock, that's when it leaves the try section. So a process is said to be in the critical section when it is the exclusive possessor of the lock. And when it no longer needs the lock, the process executes the exit section and to give up the lock so that someone else can have it. And after that, it goes back to the remainder section where it remains until it again gets interested in the lock. So this is the way a process is modeled. And as we know, the mutual exclusion requirement is the most important requirement, and it simply says that at most one process is in the CS, critical section, at any time, right? The other natural properties are starvation freedom, which simply says that if a process is in the try section, then it should eventually enter the critical section. And the bounded exit is a very natural property. It says that every process should be able to complete the exit section in a bounded number of its own steps. Alexei, in response to a question you had asked about weight freedom, I called it bounded here. I could have just said the requirement is a weight-free exit. Namely that each process completes the exit section in a bounded number of its own steps, regardless of how its steps interfere or interleave with the steps of other processes. So weight-free requirements come up in all sorts of problems. Now it's coming up in the context of defining the requirements for a lock problem, mutual exclusion problem. So weight freedom as a concept shows up in a lot of places. This would be an example, and we'll come across another example soon. Okay, so these are the three natural requirements of the problem. And past research, as we know, the traditional model assumed that processes do not crash, and solution was they do not crash, but they could be arbitrarily fast and slow. So you still have to account for asynchrony, but no crashes. And the modern goal, of course, is to design a recoverable algorithm. The past research, the goal is to design an algorithm when processes do not crash, and you want the RMR complexity to be a constant. So that is the performance challenge. So what does that mean? That means regardless of how many processes are accessing the implementation, are accessing the lock, the number of RMRs induced when you are trying for the lock or exiting the lock should not be more than a constant, some constant, right? So that's the goal of the past research. And let's get a feel for what the traditional algorithm looks like. It's very, very simple. We have known these efficient constant RMR mutual exclusion algorithms for 3 decades now. So what I'm showing here is due to Granke, Thacker, and Craig from about 30 years ago. So the idea is processes, here I'm showing process Q1, Q2, Q3, processes that are interested in acquiring the lock, they simply queue up. So they have nodes, and these nodes are in a queue, organized in a queue. Okay, so Q1 is the first in the queue. Behind it is Q2. Behind it is Q3, and the organization of the structure is such that if there are 3 processes waiting, then there will be one more node, 4 nodes in the queue. All right. So there is one more node than the number of waiting processes in the queue. All right. So there is a variable called tail, which simply points to the rear of the queue, the node at the rear of the queue. Okay. So what does each node contain? Each node contains an indication of whether the token is present or not present. In this particular representation, true indicates that a token is present, and false indicates that a token is not present. Okay. So if you look at the diagram, if you look at the figure now, you will see that this node has true, meaning it has the token. And the process immediately behind this node is the process Q1. So in this algorithm, each process simply queues up by putting its node, by inserting its node at the end of queue, and it simply waits until it finds a token in the node that's immediately in front of it. So what is the only process here that has a token in front of it? That would be Q1, right? So Q1 finds the token in front of it, and therefore it goes into the critical section. It goes into the critical section. Q2, Q3, for them, the node in front of their node does not have the token, so they simply wait for the token. Okay, so let's see how things progress from this point on with this simple animation. Okay, so yeah, so Q1 is in the CS because it's the node in front of it has the token. So let us say Q1 is exiting. If it is exiting, what should it do? It should deposit the token for the guy behind it. So that's exactly what is going on now. Q1 will write true, deposit a token for the sake of Q2. So Q2, of course, is spinning, waiting for the token to appear here, and now it sees that token, and therefore Q2 will enter the critical section. All right. And now what? Now at some now let us say a new process P, which is in the remainder section, wants to acquire the lock. Then how does that happen? As follows. P takes its node, it will initialize it to false. So it puts false in its node to show that, well, there is no token yet. And then now what should P do? It should enqueue itself. It should insert itself into the queue. What does it take to insert itself into the queue? The tail pointer will have to switch to this node. But then P also needs to know who is ahead of it. So P needs to know a pointer to this node, even as the tail is changing to this, right? So how can both of these things happen at once atomically, right? This is where the fast instruction comes very handy. So look what happens. So tail changes to that, and so tail changes to P's node, and simultaneously P learns the predecessor node, a pointer to the predecessor node. So once, remember that we are still dealing with the model in which there are no crashes, just the traditional model. So don't worry about crashes. So now P simply waits until the node at pred P, namely this node, contains true. Okay, so suppose things move on and Q2, which is in the CS, leaves the CS, depositing a token that will then enable Q3 to enter the critical section. So Q3 will go into the critical section. Eventually, let's say Q3 leaves the critical section. When it leaves the critical section, it deposits the token for the guy behind it. So P will now see it and go into the critical section. Okay, it will go into the critical section after seeing this token. Now let's say P is exiting. What should P do when it exits? Clearly, it should deposit a token here for the sake of anyone who is either already behind it or will come behind it in the future. That's one thing it needs to do, right? So it will need to deposit true here. But once it deposits true here is a very important observation. Pay attention to this. Once it deposits the token here, P is forced to leave this node behind in this queue, because that token which it leaves in this node has to be visible to anyone who comes behind it in the future. So when P walks away from the protocol, from the exit section, it no longer can walk away with its node. So what can P do if it in the future wants to come back and execute the protocol? It no longer has its node. So here comes a very brilliant observation, originally due to Craig. And Craig noticed, look, just as P is having to abandon its node for the sake of the guy that will come behind it, the guy in front of P would have abandoned this node when he left the protocol, and therefore, as P leaves this node behind in its exit section, it can walk away with the node in front of it as if it is its own node for the purpose of the future. Understand? So that's a very nice observation made by Craig. And so the exit section simply consists of writing true in this node and now walking away with this node, meaning the node pointed by pred, which is this, becomes P's node when P exits. So that's the protocol. That's the protocol. That's the traditional algorithm. And here is the beauty of this traditional algorithm. By the way, the algorithm I showed you is for the model I described, which is for machines that have caches. It turns out, although that's not the subject of our class today, another model was also considered by people. It's the distributed shared memory model, where processes don't have caches, but shared memory itself is partitioned across processes. It turns out Malacramy and Scott to generalize this algorithm, which is only for cache coherent architectures, into an algorithm that works both for cache coherent architectures as well as for distributed shared memory models. And so their lock, MCS lock, is very popular, and it set, in fact, a gold standard for mutual exclusion lock, because it has three terrific properties. One property is that it has O of 1 RMR complexity. It has O of 1 RMR complexity, which is, of course, what we want. The second and by no means a lesser property is the lock is tremendously flexible in the sense that it can be accessed by any number of processes, arbitrarily many processes of arbitrary names. There are many distributed algorithms that are designed for just n processes, where n is some number that you have to set the fix at the time the algorithm is launched, is deployed. But unlike such algorithms, this algorithm, the lock, does not have to know how many processes will access it. And arbitrarily many a number of processes can access this lock. So that's a great advantage. And the third advantage is not only is it RMR efficient, optimal, it's also very, very space efficient. If you implement m locks, a total of m locks, each to be shared by n processes, it takes only O of m plus n space, as opposed to what is typical for many algorithms, which is O of m times n space. This takes only O of m plus n space, of course, assuming that no process holds on to more than one lock at any time. Okay? So, so this is the gold standard that MCS set, but MCS has one drawback too. MCS is about 30 years old, by the way. It has a drawback too. It has an unbounded exit section. It does not have a bounded exit section, but there have been many algorithms that improved, that got rid of this shortcoming of the MCS algorithm. The one by Craig and several subsequent ones. But each one had some minor a kink or the other that you could be not entirely happy about. And in fact, I mean, at the start of this year, 6 months ago, I was fortunate to have an opportunity to publish a paper with my daughter and son. And the three of us published an algorithm that essentially, I mean, that we hope is the culmination of this effort of building on the MCS locks, something that meets the gold standard and has several other nice properties. So in any case, for the traditional model in which there are no crashes, the short story is that there are wonderful locking algorithms, mutual exclusion algorithms. And the grand challenge for us then is, can we design a recoverable algorithm? Can we design a recoverable algorithm, namely an algorithm, a mutual algorithm for the crash and restart model that meets the same gold standard, that has all these three properties? Okay, so that's the challenge. And the happy answer is yes. Okay, the happy answer is yes. And let me show you an algorithm now that has these properties. But that algorithm, while it meets the gold standard, is going to have a shortcoming. I will not announce the shortcoming yet, but I'll announce. We will see it together very soon. But let's look at that algorithm. Then we will look at another algorithm that will overcome that shortcoming, and that would be our final algorithm for the talk. Okay, so that's where we are headed. Therefore, we are now just about to look at recoverable algorithms for mutual exclusion, those that can tolerate crash failures. Before we can look at the algorithm, let us just be clear as to what the specification of the problem is the moment you have the crash restart model. Okay, so remember that a process can crash at any time. A process can crash at any time, and if it is the system-wide crash, then all processes together can crash at any time. And when a process crashes, all of its CPU registers, including the program counter, lose their contents, as we know, as we discussed. and every crash process eventually restarts. And when a crash process restarts, it begins executing the trisection from the very start. Okay, answering or addressing Peter's question with respect to the cast read recoverable implementation. Peter, in this implementation, we are not going to assume any ugly interface like the one we assumed there that you did not like. For instance, I mean, when a process invokes the trisection, it just invokes the trisection. There are no parameters. Okay, so we assume that the shell itself is non-volatile, meaning persistent. So memory contents are not lost when processes crash. All right. So fine. What are some special properties that we should strive to ensure in the context of mutual exclusion algorithm where processes crash and recover? So one very crucial property was identified by Golub and Ramaraju, who spearheaded work on this problem and on recoverable algorithms. They made this very nice observation that this is a very desirable property, which they call critical section reentry. It simply states that if a process P crashes in the critical section, no other process enters the critical section until P restarts and re-enters the critical section. And why is this important? It's important because suppose I am the process P and I am in the critical section. And in the critical section, I'm manipulating some data structure. And so in the middle of that critical section, as I'm manipulating this data structure could be in some inconsistent state. So suppose I crash at that point in time. Then this data structure is in a very dirty state. And the only one that can repair it, you can conceive, is me. So I should have the chance to get back and clean up my work, be done with my critical section before anyone else enters the critical section. Okay, so that's what this critical section reentry property, CSR property of Golub and Ramaraju captures. Now, subsequently, my student Anup Joshi and I came up with another interesting property, which I'm just about to show. The motivation is this. Suppose I was the one that crashed when I was in the critical section. Then none of you can enter the critical section until I come back into the critical section, right? When do I have a chance to come back into the critical section? Only when I restart and I am put at the start of the protocol. So once I restart and I am put back at the start of the protocol, at the start of the trisection, it is the case that nobody in the meantime could have gone into the critical section and nobody can go into the critical section. So everyone is waiting for me to get into that critical section, clean it up. You guys have a chance to go into the critical section, right? So when that is the situation, is it not desirable that I should not be blocked by anybody in the world from entering into the critical section? That's very important, right? Because I should be able to walk into it. Nobody should be able to block me, because blocking me is very undesirable, because until I get in there, none of you can do anything. I mean, you can't progress with the protocol. So that brings in this following natural requirement, which is wait-free recovery to critical section, which simply says that once a process P restarts after crashing in the critical section, if P takes steps without crashing, P should be able to enter the critical section in a bounded number of its own steps, regardless of how its steps interleave with the steps of other processes. So this is the wait-free recovery. Again, addressing Alex's thing as to the relevance of wait freedom. The relevance of wait freedom is not just to purely realize wait freedom in the implementation of shared objects, but it comes up in other contexts, such as, for instance, here. Okay. So now that we understand what it means to solve the mutual exclusion problem in the crash restart model, let us look at an algorithm. All right. This is probably a good time to pause for very briefly, for just a minute, to answer any clarifying questions before I show you an algorithm.
ಅದು ಮುಂದಕ್ಕೆ ಬರುತ್ತೆ
ಸುಬೆಟ್ಟಾಸ್ತಾ ಇದೆ ಮುಂದಕ್ಕೆ.
I do not see any questions. I think we could.
Very good. Very good. So I'll move on. So this is an algorithm that meets the goal, although it has a bad shortcoming that we will see. This is due to this is my work with my student Joshi and my son Siddhartha Jayanti from a couple of years ago. Its shortcoming is that it uses an instruction that's not really available on real machines. This instruction is FASAS. This FASAS instruction was first used by Golub and Handler. But it's an unrealistic instruction. But it is instructive to look at this algorithm anyway, just to get a sense of, what's going on. So what is this FASAS instruction? So this FASAS instruction takes two shared variables, x and y, as arguments, and a register, the process's internal register u, and it simply has the following effect. It stores the value in the register into x, and whatever was the previous value of x, it will shift it into y. Again, you see what's going on? It'll store the value in the register into x, and whatever was in x just before this storing is moved to y. X and y are both shared variables. Okay, so that's the FASAS instruction. It turns out if you have this instruction, you are lucky. It's not too hard to implement mutual exclusion for the crash model. And how does that go? Let me give you a quick sketch. As before, processes are lined up. In the past, the convention was that if in a node you had true, that means the token is present, and if it's false, the token is not present. But in this algorithm, the convention is similar but slightly different. If you have a non-nil value, that means the token is present. If you have a nil value, that means the token is not present. So a token is not present here, but a token is present here. Okay. In the given picture, the tokens are there here and here and here, but these processes have already exited, so that there is a token lying there is of no significance. The process currently still waiting in the queue is only Q3, and what is it waiting for? It is waiting for a token to appear here. There is a non-nil here, and therefore a token is present here, and therefore Q3 is in the critical section. Okay, I'm starting with the understanding of the algorithm from this initial configuration. So Q3 is waiting, is in the queue, but it finds a token in the node in front of it because it's non-null, so it's in the CS. Okay, so now what can happen? Well, let's say a new process P comes along, and it wants to acquire the lock, so it wants to insert itself into the queue. So here, in this algorithm, we will maintain, for each process P, we will maintain two persistent variables. I'm calling it mine P and pred P. Okay. Initially, mine P basically points to the node that P owns at the moment. So currently P owns this node at the moment, and therefore mine is pointing to that. Initially, pred also points to the same node. Okay. We will see how these nodes interact soon. Okay. So P is a new process that wants to join the queue. So currently things look like this for P. And what does P do? Well, P reads the persistent variable mine into its local register. So it has a pointer now to its node. Now it puts nil in that node. This is to make sure that anyone else who might come behind it after it succeeds in getting itself into the queue will not right away see a token there. So it puts a null, fine. And now, in the previous algorithm, what did we do? In the traditional algorithm, what did we do? We used the fast instruction. And what did the fast instruction do? It simply updated the tail pointer. It simply updated the tail pointer to this node and returned to P the predecessor node. So return to P a pointer to this node. But the pointer to this node is returned and placed where? It is placed in a register for process P. But what happens if process P now crashes? If P now crashes, that's a disaster, right? Because P would permanently lose this pointer to its predecessor node. So P would find itself in this unfortunate situation where it's already in the queue. It inserted itself into the queue, but it has forgotten and has no means of ever recalling what its predecessor node is. That is very unfortunate. So that should be avoided. And how could you avoid it? Well, one way to avoid it is, instead of manipulating things with fas, use this fasas instruction. And what does fasas instruction do? Fasas instruction will do two things. Look at the animation carefully. Well, my animation was bad. This link broke. Fasas would cut out this link and update the tail to this node, and simultaneously put what was in tail into pred P. So pred P, which is a persistent variable as opposed to being a register which is not persistent, now is pointing to the predecessor node. So two good things happened. Tail has been properly updated, and the persistent variable is now storing the predecessor node, so P has no danger of losing it. So, well, P will now read what is in pred P and simply wait until it finds a token there, so until it becomes non-null. And when that happens, when non-null gets put here by the process Q3, which is exiting, P will find it and will enter the critical section. It will enter the critical section, right? And when P exits, what should it do? It should leave a token here, and it should, because it has to leave this node behind, it should walk away with the predecessor node, right? Just as before. So how can it do two things at once? So it needs to do two things at once now. It needs to leave the token here and switch its node to this. So it does that again with the fasas instruction. So this fasas instruction that I have written here enables it to switch, to put non-null here, as well as adopt this as its new node. Okay, now it's able to walk away. So, so all is great, but what happens if during the protocol at some arbitrary point process P crashes and it subsequently restarts? How does it recover? The code is here. When it restarts, it simply loads up its registers with the values in the persistent variables mine and pred, and it can compare whether mine and pred are the same or not. So it just checks these two registers against each other and whether they are the same or not. I should have put the register names instead of the persistent variable names here, but it doesn't matter. But it's checking whether these are the same or not. If they are the same, then it knows that it is still in the trisection before the fasas, so it'll just go to line 1. But if they are different, then it knows that it is either critical section or at the very start of the exit section. So it'll go back to the critical section. Assume critical sections are idempotent, which they have to be if you want recoverable mutual exclusion. So it'll go back to the critical section, execute it if necessary, and then does the fasas to complete the operation. So that's the recoverable algorithm. So it meets the gold standard, but it's not. it's not a realistic algorithm, so we don't like it. It uses the fast-as instruction, right? So the real challenge then is fast-as is unrealistic, and so is there of an RMR? Is there an algorithm that meets the gold standard while using only realistic operations such as cast, fast, and maybe fetch and add, and so on? And the nice answer is yes. Okay, but when I say yes, I have to say one thing. I told you that there are two crash restart models, right? One is a model where individual processes can crash at arbitrary points, and second is a system crash model where if at every crash event the entire system crashes. So when I say yes, I mean that we have an algorithm. We have algorithm for a system crash model that meets the gold standard. So where the entire system crashes at every crash event and not just some individual processes. For the individual processes, we have an algorithm, any algorithm that we have using realistic primitives. The algorithm that I have just shown you, the one with fast-as, deals with both models of failure, both models of crashes, but it's not realistic because of the instruction that it's using. So if you want to confine yourself to algorithms that use only realistic instructions, then we do not know of any algorithm so far that meets, there doesn't exist any algorithm so far that meets the gold standard. In fact, any algorithm that I can think of is short of the gold standard by at least two requirements, not just one. They can support only n processes, and as opposed to arbitrarily many processes, and also there is no O of 1 RMR complexity algorithm. The best we know is O of log n over log n. These algorithms are due to Golub and Handler at POTC 17, subsequently improved and developed further by me and my student Joshi and son Siddhartha Jayanti. So we won't go into those algorithms. My aspiration is we have just 5 minutes, maybe 4 minutes of which I can use, or 3 minutes, I don't know. I want to very quickly show you just the sketch of the algorithm. Again, you can't believe that it is correct in the short time that we have, but I just want you to have a feel for it. This is for system crashes, okay? Where is it? Is it a different animation? 1 second. Okay, fine. Okay. Here is the intuition for the algorithm. The intuition for the algorithm is, what are we trying to do? We are trying to implement a recoverable lock script L, right? So in this algorithm, how we do that is, imagine that you have an infinite supply of traditional locks. We will use this infinite supply of traditional locks to implement this recoverable lock L. You might say, hey, if you are using infinite supply of traditional locks, that is unrealistic. So from using fast-as, you are now making a new unrealistic assumption. No, I'm saying infinite number of locks only to get your intuition going, but it turns out the actual algorithm itself requires only 3 locks, 3 traditional locks. You don't need an infinite supply, but for now, assume that you have an infinite supply to understand the sketch of the algorithm, okay? So if you have an infinite supply, the idea is processes start using lock L1. But if a system crash occurs, then L1 becomes unusable and they will migrate to lock L2. If a system crash occurs, L2 becomes unusable, they'll migrate to L3, and so on. So there is a persistent variable in the algorithm called seek that keeps track of the latest lock, latest traditional lock that is currently under use. Okay. In addition, in the algorithm, each process P has a persistent variable SP, which is process P's image of P's recollection of the latest lock out of L1, L2, L3, and so on that P has seen. Okay, and there is one other variable we need, which is active P, that basically indicates whether P is an active process or not. Okay, just using this representation, it turns out we can do things. I'll quickly go over the code again, just to give you a sense, but obviously not to convince you of anything, given that we have only 2 minutes. So with the check that it is active and that the number that it is aware of is in fact the latest number, P realizes that the latest lock seek must have crashed, and therefore it advances to the next lock. And having done so, if it checks whether, by the way, there is one extra variable I forgot to tell you about, CS owner, which has the name of the process that's currently in the CS. If no process is in the CS currently, it'll have bottom. Okay, so if P is the CS owner, it'll just directly go to the critical section. If that's not the case, P starts executing the protocol, the rest of the protocol, by remembering that it has become active by reading the latest lock number that it should access, and then it will actually try to acquire that lock number, LSP. It will try to acquire it. If it acquires it, it will check for whether the CS is empty or not. It's possible that some tail process crashed, and therefore the CS is not empty. And I see that your time is the time is up, right? So it is fine. I mean, so we will leave it as this, just to give you a visual idea. That's the algorithm. Okay, it's not big, but we can take it up in the discussion room yesterday. And if any of you, in fact, would like to try, knowing that there is a short algorithm, if you would like to try what that algorithm is and come up with suggestions tomorrow, that would be great either. So let me stop there.
Okay, thank you, Prasad, for the great lecture.
Thank you very much. And so just to remind that the slides of Prasad's lecture are online, so you're welcome to consult the algorithms he described today and come with questions. So the discussion room for tomorrow is in the afternoon at 3 p.m. Moscow time. Just a reminder, so the next session for us the next lecture is going to be Christian Kashan's second half of his lecture tomorrow morning at 10:30 a.m. Followed by his discussion room, which is going to take part of his slot. So it's going to be before Prasad's lecture and before the lunch break. And I think we don't have any questions for now, and please come with your questions tomorrow. And thank you, Prasad, again for joining us at this summer school.
Thank you. It was a pleasure, and I'll see you all tomorrow.
Thank you.
Thank you.
Bye. Bye-bye. Your being there to moderate was very helpful. So thanks to Alexei and Peter. Bye-bye. See you tomorrow.
We'll be there tomorrow. Yeah. Bye-bye.
Bye.